So far we have seen some basic types of values in Python. We began with the numeric types, which were divided into two categories, int and float. So int represented whole numbers or integers, and float represented values which have a decimal point. And for these we had arithmetic operations such as plus, minus, times, divides, and also other functions which we can import using the math library which is built into Python. Then we introduced a new type of value which may not be so familiar. For logical values, true and false, which are of type bool, we can operate on these values using functions such as not, which negates a value, makes it the opposite, and or. And when we do comparisons between numeric values, for instance, the outcome of such a comparison is typically a bool value. And we can combine these comparisons using not and to make complex conditions. In the previous lecture, we looked at strings. So strings are used to represent text. A string is of type str. It is a sequence of characters. And since it is a sequence, we can talk about positions in the sequence. So the positions start numbering at 0 and go up to n minus 1, where n is the length of the string. If we say s square bracket I for a string value s, then we get the ith position using this numbering convention. And a slice gives us a subsequence, a string from position I to position j minus 1, written s square bracket I colon j. The basic operation we can do with strings is to glue them together using the plus operation. So plus means concatenation for strings and not addition in the arithmetic sense. We can extract the length of a string using the len function, and we said that we will look at more complex string functions later on. Today we move on to lists. A list is also a sequence of values, but a list need not have a uniform type. So we could have a list called factors, which has numbers 1, 2, 5, 10. We could have a list called names, which has Anand, Charles, and Muksit. But we could also have a list which we have called mixed, which contains a number, a boolean, and a string. Now, it is not usual to have lists which have different types of values at different positions, but Python certainly allows it. So while we will normally have lists which are all integers or all strings or all boolean values, it could be the case that different parts of a list have different types. A list is a sequence in the same way as a string is, and so it has positions 0 to n minus 1, where n is the length of the list. So we can now extract values at a given position, or we can extract slices. So in this example, if we take the list factors and we look at the third position, remember that the positions are labeled 0, 1, 2, 3, then factors of 3 is 10. Similarly, if we take the list mixed and we take the slice from 0 to 2 minus 1, then we get the sublist consisting of 3 and 2. As with a string, the length of a list is given by the function len. So len of names is 3 because there are 1, 2, 3 values in names. So remember that length is just a normal length, whereas the positions are numbered from 0 to n minus 1. So there is one difference between lists and strings in what we have seen so far. We said that there was no concept of a single character. So in a string, if we take the value at a single position, or we take a string, a substring of length 1, we get the same thing. So if we have the string h, which has positions 1, 2, 3, 4, 5, oh sorry, 1, 2, 3, 4, so that is length 5. And if we ask for the 0th position, then this gives us the letter h. But the letter h in Python is indistinguishable from the string h. Similarly, if we ask for the subsequence from 0 to 1 but not including 1, then again we get the string h. So in one case, it's as though we constructed a substring of length 1. In one case, we got a single character, but Python does not distinguish. So h of 0 is actually equal to, as a value, the slice h 0 colon 1. Now this will not happen with a list in general. So if we have a list, right, a list consists again of positions 0, 1, 2, 3 say. And now if we take the 0th position, we get a value. We get the value 1. We don't get a list 1. On the other hand, if we take the slice from 0 up to and not including 1, then we get the sub list of factors of length 1 containing the value 1. So factors of 0 is 1, factors of 0 colon 1, the slice is also 1, but here we have a single value and here we have a list, and therefore these two things are not equal to each other. Right? So just remember this, that in a string, we cannot distinguish between a single value at a position and a slice of length 1. They give us exactly the same type of value and the same value itself. Whereas in a list, a slice of length 1 is a list, whereas a value at a position is a single value at that position. Now, lists can contain other lists, so this is called nesting. So, for example, we can have a nested list. So, this contains a single value at the beginning, which is another list. So, this is position 1, this is position 0, this is position 1, and this is position 2. So, position 1 is a single simple value, an integer 0, an integer 4. Position 0 is a list which in turn has itself two positions 0 and 1, and the value at position 1 is itself another list, so it's a third level of nested list which has a single value 37. Similarly, the value at position 2 is itself a string, and therefore this is a sequence and it has its own positions. So if we look at this example, then we can see that if we want to look at the 0th position in nested, then as we said, we get this value, and this value consists of a list itself containing 2 and the list containing 37. On the other hand, if we ask for the first position, position number 1, then we get the value 4. And now if we look at the position 2, which is this list, then in that we look at the 0th position, which is this string. And in that we look for the third character, which is 0, 1, 2, 3, this L. Right? So nested of 2 takes us to the last value in the list nested. In that we look at position 0, which is the first value in the nested list. And in that we look at position 3, which is the third character in the sequence contained in that position. And we get the character L, or the string L actually. So in the same way, we can also take slices. So we can take the 0th position, which is this list, and then we can ask for the slice starting at 1 and going up to but not including 2. So that means we start with this value, and so we get the list containing the list 37. So notice that the inner list is the value, right? So this is the value that lies between position 1 and up to position 2, and the outer list is because when we take a slice of a list, we get a list. Right? So this is a sub list of this list 2, list 37, which gives us just the list 37. We have dropped the value 2, but we get a sub list. So this is what we mentioned before. For lists, a slice gives us back a list. So let's just confirm that these things behave as we said. So here we have just loaded the Python interpreter with that example. So nested is this list. Okay, and if we say now nested 0, we get 237. If we say nested 1, we get the value 4. Now if we say nested 2, we get this list. So if we say nested 2, 0, then it drops the list and just gives us a string. And if we say nested 2, 0, 3, then we get the string L, as we said before. And then we said that we can now update, for instance, nested we can look at nested 0 and take the slice 1, 2, and this goes to the first list and gives us the list containing 37. So the outer list is because it's a slice, and the inner one is because the value in position 1 of the first item in the list nested is itself a list containing 37. So one fundamental difference between lists and strings, or indeed any of the values we have seen before, is that a list can be updated in place. So if we have a list nested as we had before, and we say nested of 1 is 7, remember when we try to change a position in a string, we got an error. So we can't change the second L in hello to P just by saying that we want position 3 to be replaced by P. But for a list, this is allowed. So if we want the 4 to be replaced by 7, we can just say nested 1 equal to 7. And this will give us the list 237, 7, and then hello. And we can do this inside as well. So we can say that we want to go into this list, which is nested 0. Then we want to go into this list, which is nested 0, 1. And then we want to go into this value and change this value. So we want to change the value at the position 0 of the nested list at position 1 of this initial value. So we say nested 0, 1, 0 equal to 19. And this changes that 37 into 19. So this is allowed. So what we say in Python notation is that lists are mutable. Mutable, so mutation is to change. So a list can be transformed in place. We can take a list and change its structure. Unlike a string, if we try to change a string, we have to actually construct a new string and reassign the name. But in a list with the same name, we can update parts of it without affecting the other parts. So once again, let us check that what we have done actually works. So if I say nested of 1 is equal to say 7, then the list nested, the same name, now has a 7 in place of the value 4. If I say nested of 0, which is the first list, at 1, which is the second nested list, at 0 is equal to 19. Right? So this says go in and turn the 37 into a 19. And indeed, this does happen. Right? So this is the difference between lists and strings. Lists are mutable values. We can go in and change values at a given position without affecting the name and the rest of the list. It is important to understand the distinction between mutable and immutable values because this plays an important role in assignment, and as we will later see, it also plays a major role in what happens when we pass values to functions as arguments. So let's look at what happens when we assign names. So suppose we go through the following sequence of assignments. So we initially assign the value 5 to the name x. Then we assign the value in the name x to the value y. And then we reassign x to 7. Right? So we started with x being 5. Then we said y is also 5 because y is the value of x. And now we changed x to 7. So the question we would like to ask is, has the value of y changed? So let us do this and see what happens to y. Right? So let's start with x equal to 5, y equal to x. So if we ask for the value of y at this point, it is 5 as we expect. Now we change x to 7. So the question is y 5 or y 7? And indeed y is still 5, and this is perfectly natural as far as our understanding goes, that what we did when we set the value of y to the value of x was that we made it 5. We didn't say make it the same value as x forever henceforth. So as we saw, the value of y actually did not change. And the question is, why should it change? After all, it seems natural that when we assign a value to the value of another name, then what we are actually doing is saying, copy that value and make a fresh copy of it. So x is 5, well, make y the same value as x currently is. It doesn't mean that make y and x point to the same value. It means make y also 5. So if x gets updated to 7, it has no effect on y. So this question actually is not so simple. While our intuition says that assignment should always copy the value, okay, in some cases it does happen that both names end up pointing to the same value. So for immutable values, we can assume what our intuition says, that whenever we assign a name a value, we get a fresh copy of that value. So this applies to all the types we have seen before today's lecture, namely int, float, bool, and string. These are all immutable. So if we do the kind of assignment we did before, where we assign something to x, then make y the same value as x, and then update x, y will not change. So updating one value does not affect the copy because we have actually copied the value. However, as we have pointed out, lists are a different beast from strings, and lists are mutable. So it turns out that for mutable values, assignment does not make a fresh copy. So let us look at the following example. We first assign, say, the list 1, 3, 5, 7 to the name list 1. Then we say that list 2 is the same as list 1. So if we had this copy notation, now we would have two copies of the list. Suppose we now use the mutability of list 1 to change the value at position 2, namely this value, to 4. Okay? The question is, what has happened to list 2? Is list 2 the same as before, namely 1357, or has list 2 also become 1347 like list 1? So let us see what happens in the interpreter. So let us run this example in Python. So we say list 1 is equal to 1357, list 2 is equal to list 1. So list 2 is indeed 1357. Now we update in place list 1, 2 to be equal to 4. So we say that list 1 is 1347. The 5 has been replaced by 4. So the question we are asking is, has this affected list 2 or not? And contrary to our intuition that we have that values are copied, in this case, list 1 has indirectly affected the value of list 2 as well. So why does this happen? So list 2, 2 is also 4, and that is because when we actually make assignments like this from one name to another name, and the other name holds a mutable value, in this case the only mutable type that we have seen so far is a list, then instead of saying that there are two copies, we actually just say that list 1 is pointing, if you like, to a value of list 1357, and now we also have another name for the same list, namely list 2. So if we go and change this value to 4, then list 2 also has the same value 4 at this position. So there's a fundamental difference in how assignment works for mutable and immutable types. For mutable types, we can think of assignment as making a fresh copy of the value, and for immutable types. And for mutable types, assignment does not make a fresh copy, it rather makes both names point to exactly the same value. So through either name, if we happen to update the mutable value, the other name is also affected. So this is something which we will see is useful in certain situations. But what if we don't want this to happen? What if we want to make a real copy of a list? So recall that a slice takes a list and returns us a sublist from one position to another position. The outcome of a slice operation is actually a new list, because in general we take a list and we will take a part of it from some intermediate position to some other intermediate position. So obviously the new list is different from the old list. So we also saw that when we looked at strings, that we can leave out the first position or the last position when specifying a slice. If we leave out the first position as this, then we will implicitly say that the first position is 0, so we start at the beginning. Similarly, if we leave out the last position like this, then we will implicitly assume that the last position in the slice is the length of the list or the string, and so it goes to the last possible value. So if we leave out the first position, we get a 0. If we leave out the last position, we get the length. So if we leave out both positions, we just put a colon with nothing before and nothing after. Logically, this becomes 0 and this becomes the length, right? So we have both characteristics in the same thing, and we call this a full slice. Now let us combine this observation, which is just a shortcut notation, with this observation that each slice creates a new sublist. So what we have is that L with just a colon after it is not the same as L. It's a new list created from the old list, but it has every value in L in the same sequence. So this now gives us a simple solution to copy a list. Instead of saying list 2 is equal to list 1, which makes them both, so remember, if I don't have this, then I will get list 1 and list 2 pointing to the same actual list. So there will only be one list of values and will point to the same thing. But if I do have this, then the picture changes. Then what happens is that the slice operation produces a new list which has exactly the same length and the same values, and it makes list 2 point to that. So therefore, after this, list 1 and list 2 are disjoint from each other. Any update to list 2 will not affect list 1. Any update to list 1 will not affect list 2. So let us see how this works in the interpreter to convince ourselves that this is actually the way Python handles this assignment. So as before, let us start with list 1 is 1357, and list 2 now let us say is the slice. So now if I update list 1 at position 2 to be 4, then list 1 looks like 1347, but list 2, which was a copy, is not affected. Right? So when we take a slice, we get a new list. So if we take the entire list as a full slice, we get a full copy of the old list, and we can assign it safely to a new name and not worry about the fact that both names are sharing the value. So this leads us to a digression on equality. So let us look now at this set of Python statements. We create a list 1357 and give it the name list1. And we create another list 1357 and give it the name list2. And finally, we assign list3 to be the same value as list2. And this, as we said, suggests that list3 is actually pointing to the same thing. So we have now, pictorially, we have two lists of the form 1357 stored somewhere. Right? And initially we say that list 1 points to this and list 2 points to this, and the last assignment says that list 3 also points to this. So all three lists are equal, but there is a difference in the way that they are equal. So list 1 and list 2 are two different lists, but they have the same value. Right? So they happen to have the same value, but they are two different things, and so if we operate on one, it need not preserve this equality anymore. On the other hand, list 2 and list 3 are equal precisely because they point to the same value. There is exactly one list to which they are both pointing. So if we update list 3 or we update list 2, they will continue to remain equal. Right? So there are two different notions of equality, whether the value is the same or the actual underlying object that we are referring to by this name is the same. In the second case, updating the object through either name is going to result in both names continuing to be equal. So Python has, as we saw, this operation equal to, which is the equivalent of the mathematical equality, which checks if x and y as names have the same value. So this will capture the fact that list 1 is equal to list 2, even though they are two different lists, they happen to have the same value. So to look at the second type of equality, that list 3 and list 2 are actually the same physical list in the memory, we have another keyword in Python called is. So when we say x is y, what we are asking is whether x and y actually point to the same memory location, the same value, in which case updating x will affect y and vice versa. So we can say that x is y checks if x and y refer to the same object. So going by this description of the way equal to and is work, obviously if list 2 and list 3 are the same object, they must always be equal to. So if x is y, then x will always be equal to y because they are actually pointing to the same thing. But in this case, although list 1 and list 2 are possibly different lists, they are still equal to because the value is the same. On the other hand, if I look at the is operation, then list 1, list 2 is list 3 happens to be true because we have seen that this assignment will not copy the list, it will just make list 3 point to the same thing as list 2. On the other hand, list 1 is list 2 is false. That's because they are two different lists. So once again, it's best to verify this for ourselves to convince ourselves that this description is actually accurate. So let us type out those three lines of Python in the interpreter. So we say list 1 is 1357, list 2 is also 1357, and list 3 is list 2. So now we ask whether list 1 is equal to list 2, and indeed it is true. But if we ask whether list 1 is list 2, then it says false. So this means that list 1 and list 2 are not pointing to the same value physically. So if we update one, it will not update the other. On the other hand, if we ask whether list 2 is list 3, then this is true. So if, for instance, we change list 2 to be equal to 4, like we had done in the earlier example, then list 2 has now become 1347. So if we ask if list 1 is equal to list 2 at this point, as values they are false because list 1 continues to be 1357 and list 2 has become 1347. However, if we ask whether list 2 is equal to list 3 is true, that is the case because list 3 is list 2 in the sense that they both are the same physical list, and so when we updated list 3, list 2, we also updated list 3. Like strings, we can combine lists together using the plus operator. So plus is concatenation. So if we have list 1 is the values 1, 3, 5, 7, and list 2 is the values 4, 5, 6, 8, then list 3 equal to list 1 plus list 2 will produce for us the value 1, 3, 5, 7, 4, 5, 6, 8. One important thing to recognize in our context of mutable and immutable values is that plus always produces a new list. So if we say that list 1 is 1357 and then we copy this list as a name to list 2. So we saw before that we have 1357 and we have two names, list 1 and list 2. Now if we update list 1 by saying list 1 plus 9, this will actually generate a fresh list which has a 9 at the end, and it will make list 1 point there, and list 2 will no longer be the same. Right? So list 1 and list 2 will no longer point to the same object. Let's just confirm this. So in the Python interpreter, let us set up list 1 is equal to 1357 and say list 2 is equal to list 1. Then as we saw before, if we say list 1 is list 2, we have true. If on the other hand we reassign list 1 to be the old value of list 1 plus a new value 9, so this extends list 1 to be 13579. Okay, now we'll see that list 2 is unchanged. So list 1 and list 2 have become decoupled because each time we apply plus, it is like taking a slice. Each time we apply plus, we actually get a new list. So list 1 is no longer pointing to the list it was originally pointing to. It's pointing to a new list constructed from that old list with a 9 appended to it at the end. So to summarize, we have now seen a new type of value called lists. So a list is just a sequence of values. These values need not be of a uniform type. We can have mixed lists consisting of lists, booleans, integers, strings, although almost always we will encounter lists where the underlying content of a list is of a fixed type. So all positions will actually typically have a uniform type, but this is not required by Python. And we can nest lists, so we can have lists of lists and lists of lists of lists and so on. As with strings, we can use the square bracket notation to obtain the value at a position, or we can use the square bracket with colon notation to get a sublist or a slice. One new feature of Python which we introduced with lists is the concept of a mutable value. So a list can be updated in place. We can take parts of a list and change them without affecting the remaining parts. It doesn't create a new list in memory. One consequence of this is that we have to look at assignment more carefully. So for immutable values, the types we have seen so far, int, float, bool, and string, when we say x equal to y, the value of y is copied to x. So updating x doesn't affect y and vice versa. But when we have mutable values like list, if we say L2 is equal to L1, then L2 and L1 both point to the same list. And so updating one will update the other. And so we have to be a bit careful about this. So if we really want to make a copy, we use a full slice. So we say L2 is equal to L1 colon with nothing before or after. This is implicitly from 0 to the length of L1. And this gives us a fresh list with the exact same contents as L1. And finally, we saw that we can use equality and is as two different operators to check whether two names are equal to only in value or also are physically pointing to the same type.